My name is Sean Cantu. Today, we'll be talking about transmission electron microscopes. What is a transmission electron microscope? First, we'll look at a light-operated microscope, where the light source at the base projects its light beam through the sample and lenses, magnifying it for the viewer above. A transmission electron microscope, or TEM, instead of a light source, has an electron source which is powered by high voltage. These electrons are then accelerated down the column through the sample and are corrected by electromagnetic coils. The image is then captured on a phosphorescent screen or camera for the viewer. Now, let's take a look at the history of how the TEM was invented. Julius Plücker, a German scientist, pioneered investigating cathode rays. This eventually led to the discovery of electrons. Louis de Broglie suggested that electrons in all matter had wave-like properties. This was experimentally demonstrated in 1927. Ernest Ruska, in 1931, demonstrated that a magnetic coil can act as a lens for electrons. He used several of these coils in a series to build the first electron microscope in 1933. The idea of the electron microscope started to propagate as Paul Anderson and Kenneth Fitzsimmons of Washington State University constructed their first TEM in North America, 1935. Albert Prebus and James Hiller at the University of Toronto constructed theirs in 1938. With each iteration, the TEM advanced in design. In the top left, you can see some of those initial designs. After World War II, Ernest Ruska resumed his work at Siemens, where he continued to develop the electron microscope. He produced the first electron microscope with 100K magnification. Now let's take a look at some of the inner workings of the electron microscope. Electrons, negatively charged, can be affected by magnetic fields like that of the magnetic lens. Samples perceived by the electron microscope have to be ultra thin in order for the electrons to pass through and create an image. Also, the column of the electron microscope must be kept in a vacuum for air particles cause deflecting of electrons. Electrons have a wavelength that is 10 to the 5th smaller than that of light, which offers an enhanced resolution. When electrons strike atoms in an image, they show up as dark spots, and electrons that make it through would be the bright spots. While electrons cannot be detected by the human eye, they must be captured on a phosphorus screen or recorded on a CMOS CCD detector. On the right is an image of gold. What you're seeing is that those dots are gold atoms. This is a single crystal of gold at a high resolution of a TEM. This is an image of a transmission electron microscope created by Joel. It has many applications including pathology, biology, quality control, nanotechnology, polymer, and materials development. Here is a brochure showcasing Nion's many accessories for an advanced TEM. Here we see an accessory that can image electric fields, creating a 4D system on top of already the image of TM. Here we can measure the temperatures at certain points, shown by photon dispersions. Here is imaging capable at liquid nitrogen temperatures, which is useful for materials that would normally be damaged by electrons, such as polymers. Here is the electron energy loss spectrum, which acts like a fingerprint for materials and atoms. Here is an amino acid in that same EELS scanning. The EELS spectrum can actually show atom by atom positioning of each type of material. For where this fails to recognize a material, there's also X-ray scanning, which between one or the other can identify the material and its placement. The transmission electron microscope is truly an amazing piece of equipment which has allowed the advancement of technology and many other sciences just by taking a closer look.